Hi, welcome to Chapter 7, Part 2, where we're going to talk about how the size of the atom and ions varies across a period or down a group, and how the ionization energy changes. So first, before we could talk about the trends of the size, we kind of have to understand how do they measure the size of an atom. So there's two types of atomic radii. There's the non-bonding one, where they take two atoms that have collided, have not bonded, and measure the distance between the nucleus and take half of it. And then there is the bonding atomic radius, is when you have your two atoms covalently bonded and you take half the distance between the nuclei. Most of the time when we're going to be talking about atomic radii, we're going to be talking about the bonding one. So this figure down here shows the trends in the bonding atomic radius. Okay, and the trends are, if you look at the bonding atomic radius, the trends, the atomic radius decreases as you move from left to right across a period. So as you move across a period this way, and in our last video we talked about how Z effective, which is the effective nuclear charge, increases, so the force of attraction between the nucleus, which is the protons, and your valence electrons increases. So if they are attracted to each other more, because the effective is higher, the electrons will actually move closer to the nucleus, making the size decrease. So as you move across, the size decreases, the size of your atom. As you move down a group or family, so as you move down a group or family, look what's happening. Your size is getting larger, so your atomic radius is increasing. And we said in the previous video that Z effective does increase as you go down a group or family, but not by very much. So the nuclear charge really doesn't play a part in why the size changes as we go down a group. It's more about your energy levels and orbitals. As you go down the group, your energy level, you get more energy levels. So you have more core electrons. So you have more electron repulsions, which results in something we call shielding. So you're shielding the valence electrons from the force of attraction to the nucleus. And as we saw in Chapter 6, as you get to higher energy levels, and that means as you go down your group or family, there is a greater probability of being further away from the nucleus. Okay? Because your atomic orbital size is increasing. So as your energy level is increasing, your atomic orbital size is increasing, and you have a greater probability of finding your electron further away from the nucleus. So there's two main competing forces here. There is the effective nuclear charge, which is the attraction between the protons and electrons. And then there's the electron repulsions between your core electrons and your valence electrons. So when you go down a group or family, because you have more energy levels, the size of your atom increases. Well, why, as we move across a period, do the size of the transition metals, they do change, but it is very gradual. Why is it more gradual than your S&P blocks? Well, because when you look at your electrons in your D and your F sublevels or subshells, they are only moderately affected at shielding the nuclear charge. So they do shield the nuclear charge, but not very good. As a result, the effective nuclear charge experienced by the valence electrons in the D and F block do not change very greatly. And you know, as you move across, the nuclear charge increases across the row. But it's not changing. Z effective is not changing drastically as you move across the D block, because by having those D electrons, that you're not really shielding the so when you did Z minus S, this S here is not really affected that much by them. So let's talk about ions. Remember, there are two types of ions. There's cations and anions. Cations and anions. Cations are your positive, and anions are your negative. And your ionic size depends on the nuclear charge, your number of electrons, and the orbital in which your electrons reside in. If you have a cation and it's positive because you lost electrons. So when you lose electrons, you're actually going to lose, let's take lithium over here. So here's lithium, and now it became lithium plus. Notice the size is getting smaller for cations because you're losing repulsions because you're losing the electrons. So that means that if there are less repulsions, your electrons will be attracted more to the nucleus. And if you also think about it, if you take lithium, which has the electron configuration 1s2, 2s1, if it wants to become lithium plus, what happened? You got rid of a whole energy level, so the size is getting smaller. Anions, on the other side of it, are gaining electrons. Since you are adding electrons, you are adding repulsions. If the repulsions increase, it kind of pushes the electrons further away from the nucleus. So anions become larger. So let's look at something called isoelectric series or isoelectronic. So pause the video here and write the electron configuration for the following elements. Okay. So what did you notice when you wrote the electron configuration for the following elements? So let's write the electron configuration. 1s1, 2s2, 2p6. This was the electron configuration for all of these elements. So when you have something that is isoelectronic, they have the same number of electrons. They don't have the same charge, but they have the same number of electrons. So in an isoelectronic series, it's a series of elements, or ions in this case, that all have the same number of electrons. Now, if you had to predict, how would you order this from the largest radius to the smallest radius? Well, let's look at each of these elements and write the number of protons that are in each of them. So oxygen has 8 protons. Fluorine has 9 protons. Sodium has 11. Magnesium has 12. And aluminum has 13. So which one do you think is going to be the largest? They all have the same number of electrons. So electron repulsions here are all the same. But your effective nuclear charge will be different because you have more varying number of protons. So the species that has the least amount of protons will have the smallest Z effective and will be the largest. So that would be oxygen. Then fluorine. Then sodium. Magnesium. And aluminum will be the smallest because it has the most amount of protons. So it will have the strongest force of attraction to the nucleus. So if you see here, we were right. Here oxygen has the largest and aluminum has the smallest radius. The greater your attraction to the nucleus, the smaller your atom because the electrons will move closer to the nucleus, okay? So an isoelectronic series is when ions have the same number of electrons. Your ionic size decreases with increasing nuclear charge. So the next topic we're going to discuss is ionization energy. Ionization energy is the minimum amount of energy required to remove an electron from the ground state of an atom or ion. And you could remove more than one electron. The first electron that you move would be considered your first ionization energy. The second one would be your second ionization energy. If it is very hard to remove an electron, your ionization energy, I'm just going to abbreviate it, IE, is high. So the harder it is to remove an electron, the higher your ionization energy, because you need to put more energy in to remove it. So it requires more energy to remove the second electron, the third, so on and so forth. Okay? When all of your valence electrons have been removed, it will take a significantly larger amount of energy to remove a core electron. And you can kind of see that. So remember, sodium ends in an S1. So the first electron, it's going to lose, no biggie. But look at the second one. It's an order of magnitude of 10, because now you're trying to remove the inner shell electrons. And if you look at where this line kind of separates it, you can determine the charge of the ion that's going to form. So sodium forms a +1 ion, it loses 1. Magnesium loses 2, so +2. Aluminum +3, because after the third one you have a huge jump. So it's kind of interesting. You can look at that to figure out your most stable ion that you're going to form. So what are the trends in ionization energy? Well, as you go across a period, your ionization energy increases. And as you go down, your ionization energy decreases. Which means that as you go from left to right, it gets harder to remove an electron. And think about it. When you look at the periodic table, you have the metals, and as you move to the right, you go to your nonmetals. Metals like to lose electrons. Nonmetals would rather gain, so they do not want to lose electrons. So it kind of makes sense that your ionization energy gets higher as you move across a period. In your S&P block elements, you tend to see a large range of values for ionization energy. Again, in your D and F block, you're going to see small variations, and that's the same reason that we described that the atomic radius changes slightly in the D and F block. So what factors influence our ionization energy? Well, it's kind of the same thing we were talking about when we talked about atomic radius. Your effective nuclear charge, Z effective, plays a significant part of this, because that is related to the force of attraction between the electron and the nucleus. If the force of attraction is very high, Z effective is very high, then it's going to be very hard to remove an electron. So if your Z effective is high, you have a large force of attraction between your valence electron and nucleus. So it will be hard to remove an electron. So your ionization energy will be high. So remember, there's two competing forces here. So Z effective is the nuclear charge, and then there's the average distance of the electrons from the nucleus. And as we go down a group, our electrons are further away from the nucleus because of shielding. So it is easier to remove an electron. So ionization energy will be low. And see that? It's decreasing as you go down, but it's increasing as you go across. So let's look at some of the trends here. So the trends in your first ionization energy. As one goes down a column, and remember a column is a group, less energy is required to remove the first electron. And why is that? So again, as you go down, you have more energy levels. Which means you have more electron repulsions, which results in more shielding. So your valence electrons are further away from the nucleus. So the force of attraction is less. And it is easier to remove an electron because it's not held as tightly in the atom. Generally, as one goes across a row, remember a row is called a period, it gets harder to remove an electron. Why is that? Well, as you go across, your Z effective dominates, your effective nuclear charge. So the force of attraction increases. And really, I should have said this earlier. If you are on the same period, same row, you're in the same energy level. Okay? So you're all in the same energy level. If your force of attraction is increasing and you're in the same energy level, your electron repulsions are really remaining the same. So they're not really too much of a factor within a period. Your valence electrons are going to be held stronger to the nucleus. So your ionization energy is higher. Now, of course, nothing could be perfect. There are some irregularities in this general trend. And they arise when if you're moving across the periodic table within in a row or period. When you start to fill a new sublevel, you're going to get an anomaly in the trend. And when you go, if you notice here you have 2p3, here you have 2p4, and you're starting to get 2 in an orbital, so you have more electron repulsions here. And your electron repulsions kind of push the electrons a little further away from the nucleus, making the ionization energy a little bit lower. So let's talk about these irregularities. So here's a plot of the first ionization energy on the Y versus your atomic number. Okay? And the anomalies, or I like to call them blips, because they look like blips in the curve, are circled in red. And you notice the first one over here occurs when you go from beryllium to boron. And beryllium ends in 2s2, and boron goes from 2s2 to 2p1. So you're starting a whole new sublevel here. And that sublevel is because from last chapter, you know that sublevel is a little bit further away from the nucleus. So it will be easier to remove this electron. So even though in general, as we go across the period, the ionization increases, boron is lower than beryllium because you start a new sublevel and it is a little bit further from the nucleus. Then the trend starts to pick up until you get over here, which is nitrogen and oxygen. So if you look at nitrogen, it is 2p3, and oxygen is 2p4. So here you have more electron repulsion. So you're pushing that electron a little bit further away. So it's going to be easier. So you see here it's lower ionization energy to remove that electron than it will be to remove an electron from nitrogen. And these same things kind of repeat. This is just in period 2, period 3, period 4, period 5. So here, again, the first blip occurs when you go from beryllium to boron. And that's because you're going from an s to a p orbital. And the electrons are further from the nucleus in the p than they are in the s. So there's a smaller amount of repulsion by the s electrons, so it's easier to remove. Now we're talking about the nitrogen and the oxygen one. In oxygen, you're getting your first doubly occupied orbital. So the repulsions from that orbital helps to remove that electron. It makes it a little bit easier. And that is the end of part 3.